A uniform rod is going to highlight the important points of length 8 and weight W, rests in equilibrium against a rough horizontal peg at the end A is on rough horizontal ground. Friction is limiting at both A and P. The distance AP is 5. As shown in figure 4, the rod rests at an angle of theta to the horizontal where tan theta is equal to 4/3. The rod is in a vertical plane which is perpendicular to P. That just means that the rod is vertically above P. The coefficient of friction between the rod and P is 1/4, and the coefficient of friction between the rod and the ground is mu. No mention of any other forces holding the rod in place. So I'm going to go through and mark the forces on the diagram. If the rod is uniform and its weight is W, it means uniform means that the centre of mass is in the centre, so the weight acts in the centre of the rod. It's just W, not WG, because this is the weight and not the mass. And this length here is 4 meters to there and down to there. Okay, so there's a reaction force at A, so I'll call that R at A, and there's also a friction force. Now, there are no other forces holding this in place, so if the peg was smooth and the ground was smooth, this rod would just slip down gradually this way until it was flat on the ground. So the direction of motion would be that way, but acceleration is actually 0 because it's in equilibrium. I've used that and that as well. So as friction acts against the direction of motion, at the rough horizontal peg, there is friction acting in this direction, and that's friction at P. And here there's friction acting in this direction over here, and that's friction at A. So I've got the rough horizontal ground there. Friction is limiting, so that means we can use at both A and P, so we can use F equals mu R. Tan theta is equal to 4/3, so when we resolve some of these diagonal forces into components, we're going to need sine and cos of theta. So just by drawing a triangle with theta here, tan theta is opposite 4 over adjacent 3, and so the hypotenuse is 5. So sine of theta is equal to 4/5, and cos of theta is equal to 3/5. So now I've used that. The coefficient of friction between the rod and P is 1/4. So here I'm going to just write this on a different colour. Up here, mu is equal to 1/4. And between the rod and the ground is mu, so we don't know what this friction is yet. Show that the magnitude of the normal reaction between the rod and P is 0.48. I haven't marked on the reaction there yet, so that will be perpendicular to the rod, R at P. And we've got to show that that reaction force is 0.48. Now, there are lots of unknown forces here, so I want to try and minimise them. And a good way to do that is to take moments. If I take moments about A, then the distances of these forces is 0, so they're out of the equation. So now that's what I'm going to do, but I need the forces perpendicular to the rod. So there's a perpendicular force there, but I need this one into components. So the perpendicular and parallel forces are marked there, and they would go in that direction and in that direction, so down and across there. This angle is theta, so this angle here will also be theta, and so this component here is W cos theta. Now I have the two perpendicular forces, perpendicular to the rod, so I just need to take moments. I'm going to tell the examiner what I'm doing just so that the examiner can see what they're looking for to try and give me the maximum marks they can. So a distance of 5 multiplied by RP, 5 times RP, and the rod is in equilibrium, so the anti-clockwise moment here will balance out with the clockwise moment, equals a distance of 4 times by W cos theta. So I'm going to divide both sides by 5, and I've got W there, and cos theta is equal to 3/5. And when I calculate that, it works out to 0.12 W. Sorry, 0.48 W. Okay, so for the next part, B, I've got to find the value of mu. So that's the coefficient of friction here. So I'll need the reaction and the friction there. Now the reaction is vertical and the friction is horizontal, so I'm going to resolve vertically and horizontally. But that does mean that this force is fine because it's vertical, but these are now diagonal to the vertical and horizontal. I'll need the vertical and horizontal components, so I'll just need to resolve these. So if I make a right-angled triangle here, this force is going diagonally there, so up and across. And this component here, so this is theta, just using angle rules, this is also theta, and so this component here will be RP cos theta. RP is 0.48 W, so 0.48 W and cos theta. And this force at the top here, which is hard to fit in, is 0.48 W sine theta. Now this force FP here, F at P, I'm going to draw a diagonal line and a vertical line, and now I need the components here and here. So that's going upwards, so this will go that way and up like that. So this component here, this is theta, so this is 90 minus theta, and this angle here is theta. So sine theta opposite, so I've got this in terms of FP. Now that's not going to be very useful, that's an extra variable. If I can write this in terms of RP, then I'm eliminating one of the variables. So in fact, that's what I'm going to do now, because I know that the coefficient of friction is a quarter here. So using F equals mu R, F equals a quarter, this is F at P, a quarter times reaction, and reaction is 0.48 W, as we found in part A. So when I work that out, I get 0.12 W. So you can see I was jumping ahead a little bit there earlier. So now I can write this force now, Fp, as 0.12 W. So 0.12 W, it's opposite the angle, so sine theta, and 0.12 W cos theta. So now I have all the vertical and horizontal components. Sometimes it's actually good to just mark them with a coloured pen so you can see them, you don't miss any. So there's a vertical component going across, I've got another vertical component there, I've got one here, and I've got one here. And then the horizontal components, I've got one going across here, none there, one here, and one here. So now I can make my equations. So first of all, I'm going to resolve vertically. All I need to do is put that arrow to tell the examiner what I'm trying to do. So I've got a force going upwards, there, another force going upwards, one going downwards. So all these three balance with this one going downwards. So RA plus 0.48 W cos theta, 0.48 W cos theta plus 0.12 W sine theta balances out with is equal to W. So I'm going to rearrange this and put some values in for sine and cos. Equals W minus 0.48 W times cos theta, so 3/5. So 3/5 of 0.48 W, and I've also got to subtract this. Sine theta is 4/5, so 4/5 multiplied by 0.12 W. Now I'm going to factorise out the W and calculate that, and I get a value for RA of 0.616 W. I'll need that later, so I'm going to underline it. Now I found the reaction at A, so now I need to find the friction in order to find mu. So friction is horizontal here, I'm going to resolve horizontally. So I've got a force going to the right of F at A. Any other forces to the right? Yes, this one, which is 0.12 W cos theta, 0.12 W cos theta. And that balances out with the force going to the left, which is 0.48 W sine theta. 0.48 W sine theta. I'm going to just rearrange, subtracting this from both sides. So on here I'll have sine theta, which is 4/5, multiplied by 0.48 W minus this term, which is cos theta, which is 3/5, times 0.12 W. And when I factorise out the W and do that calculation, I get 0.312 W. So now I have my R and my F, I can use the equation F equals mu R. As I said, friction is limiting, so I'm allowed to use this. Mu equals F over R, which is 0.312 W over 0.616 W. And that works out to 39 over 77, because the W's cancel out, or 0.506 to three significant figures. Marks wise, so there's a method mark for clearly resolving about A. All terms included. All of the dimensions must be included, so that means you must have the distance and the force even if there's a mistake. An accuracy mark for all terms correct and finding 0.12 W. Another method mark here, an understanding mark for resolving vertically. You can have you can mix up sine and cos, and you can have sign errors, positive or negative, and still get that mark. Then a method, sorry, that B1 was meant to be here. That was the understanding mark. This is an M1. The B1 was for clearly using F equals mu R to write F in terms of W. Now you might have done that later in the question, but you'd still get that mark. So a method mark for this equation, not the B mark. And then an accuracy mark for all terms correct and finding 0.616W. So the next mark is a method mark again for resolving horizontally. Again, you can have positives and negatives the wrong way round, you can have cos and sine the wrong way round and still get that mark, as long as all the terms are included. An accuracy mark for all terms correct and finding 0.312W. Then a DM1, which is a dependent method mark for using f equals mu r, and that's dependent on showing the working to find these two values here, up here. So if you've got these two method marks, then you'll get this one. And then an accuracy mark for writing the final value either as an exact fraction or to three significant figures.